One of the hardest aspects of many statistical concepts would be how foreign or difficult they might look at from an individual who's never seen the formulas or graphs. Just look at all these equations, for example. Man, that's a lot of weird looking variables. That's why I liked line square designs, and that's why I chose this topic. To start, three-factor analysis of variables allows the user to take a treatment variable they are researching and then apply the factors that they believe can affect their data. A line square design gets its name from the line letters seen inside the boxes shown. Here, those letters represent the treatment variable an individual might be testing, while the row and columns are those blocking factors that could be affecting our data. We decide to randomly apply all these factors together so that we can lessen our error when we're producing the final number. One way I can look at this to visualize this is by this picture here. As you can see, we have separated these three factors into different areas. Then we envelop them together to produce that final output at the top that gives us the numerical number. Here's an example so I can show you guys. Here, the rate of failure of a machine is being tested. We want to find out which material gives us the least rate of failure. However, we know that materials can have different factors affect their outcome, and it's our job to see how we can incorporate these blocking factors onto our data. On the top, we know that a factor might be the origin, as countries and plants have different regulations that could affect the final material we receive. And on the left, we have the cost, as materials might cost differently depending on the day and depending on how refined or not refined they are. If we go by our data here, we can see that the rightmost column and the bottommost row produces the best output at 7 years. Another way we can use line square designs is through ANOVA testing. ANOVA analysis in the line square design is simply a lot easier to visualize and see. For example, for the sum of squares, we simply get the treatments, rows, and columns sum of squares and then add them up together for totals. Degrees of freedom would be n minus 1, and because our square is simply n squared, it's a perfect square, it'll be simply the same for each. And for our mean square, we get the sum of squares divided by the degrees of freedom, and for f sub 0, we get the mean square divided by the mean square of error. This table allows us to analyze the differences among the group means in a sample and is used widely in the field, which is why line squares aren't just a pretty picture. They're actually extremely powerful tools that are just easier to visualize. Thank you guys all for watching, and that was my presentation on line squares.